So in this video, I'm going to introduce Fermat's principle, and then we're going to talk about how Fermat's principle results in the angle of incidence equal the angle of reflection. So Fermat's principle basically states that when light is traveling between 2 points across some sort of interface, whether or not that interface be, say, a mirror or through some sort of substance, it's going to take the path that minimizes the travel time. Now it has to include a point along that interface. So in the case of the mirror, it's going to take the shortest path from the light source to some final point, as long as that path intersects the surface involved. Now this isn't, there are some exceptions to this and there are some qualifications, but this is just kind of a simplified look at this. It also doesn't exactly explain why light would minimize the travel time. We will get to that a little bit later on. So what we're going to do is show that the angle of incidence is equal to the angle of reflection based on Fermat's principle by minimizing the travel time for the light to go between two different points. So starting at point A and traveling to point B via the mirror, I've just set up a possible path. Now we're looking at all possible paths. As we know, the path that it's going to take ends up being the one where this distance and this distance are actually equal to each other and half of that length L over 2, but we're not going to assume that right off the bat. So both of my points, the starting point and the ending point, are a height h away from the mirror surface, and the path that they travel, the light travels length L1 towards the mirror and then L2 away from the mirror, and so the total travel time then is just distance divided by velocity. We're assuming this is an air, and so the light is traveling at c, roughly 3 times 10 to the 8th meters per second. So my total travel time then is given by that right there. This first term is the time to the mirror from point A, and then this time right here is how long it takes to go from the mirror to point B. Now, you notice that I can form a couple of right triangles for each leg, where this leg right here is h, this is x, and so using the Pythagorean theorem, L1 then is just the square root of h squared plus x squared. Similarly, for L2, I can draw this right triangle. Again, my legs are h and L minus x, and so this term here gives me that distance. So the next thing I need to do then is minimize the travel time with respect to the possible paths. And so I'm going to take the derivative of that travel time t with respect to this variable x. In other words, we're going to consider all possible values of x that might yield a possible path between those 2 points. And so we calculate that derivative right here and set that equal to 0. Now, something to notice is I can rewrite this part of my equation and this part of my equation in terms of the angle of incidence and angle of reflection. And so with this as my theta I measured with respect to the normal, sine theta I, sine of the incident angle, is just x over root h squared plus x squared. And the sine of the reflected angle is L minus x over root h squared plus L minus x squared. So plugging this term in for that guy and this term in over here, this is what the equation reduces down to. In other words, the sine of the two angles has to be equal to one another. Now the way that we've set up the definition of our angles, both theta I and theta r are between 0 and 90. Or I should say less than or equal to, greater than or equal to. So if that's the case, then the only solution to sine of theta I equals sine of theta r is if theta I is equal to theta r. In other words, the angle of incidence is equal to the angle of reflection.